Last time, we started to discuss phonons as lattice vibrations of ions in solids. And we took a very simple example on a one-dimensional chain where these ions and atoms are sitting along the chain with an equal distance, lattice constant A. And these lattice points everywhere can actually oscillate back and forth with respect to the equilibrium position because they are influenced by this kind of a periodic potential with the with a minima or valley near the equilibrium position. So the ions can actually vibrate due to thermal fluctuations. Then we wrote down the Hamiltonian for such a harmonic potential and along this one-dimensional chain, and we could simplify this Hamiltonian in terms of the normal mode vibration. Remember that we could diagonalize this potential matrix by some kind of a unitary transformation where this matrix T could actually diagonalize this complicated this potential form, right? Okay, and we could transform this coordinate, this real space displacement vector YL and momentum operator in real space into the corresponding operators in Q space or in the normal mode space, where this YQ is defined by such a transformation. And so that takes us from this YL to YQ by this T inverse matrix. And so is for the momentum operator. So after this kind of a basis transformation from the real space to normal mode coordinates, we could re-express the Hamiltonian for such a coupled harmonic oscillator in terms of a summation over this normal mode variables. But here is written in terms of our familiar single simple harmonic oscillator Hamiltonian, where we have a kinetic energy and potential energy. The only difference is that we sum over all different normal modes vibration, so that this is not just a single term but infinite number of terms, because for infinite number of atoms along the chain we may have infinite number of normal mode vibration, so that the sum over the normal mode vibration could contain this infinite number of terms. Nevertheless, we could take advantage of such a definition that we already learned from quantum mechanics 1, namely, we can make a linear combinations of this normal mode variables YQ and PQ, and we define a new operator which we call this A of Q or A dagger of Q. So this A of Q and A dagger of Q satisfies bosonic commutation relations. Remember, this is your homework problem, right? We could call them bosons because remember, the bosons satisfy these commutation relations, right? Okay, and these bosonic operators, as we will see later, are called phonons. So let's just use this new variables AQ and AQ dagger and rewrite this Hamiltonian from this standard form to this operator form. Okay, so the Hamiltonian now becomes this very simple form where you have the h bar omega q multiplied by the number of bosons A dagger QFQ plus the constant, which is the 0-point motion. So the only difference between this form and your familiar quantum mechanical form for a single simple harmonic oscillator is again the sum over normal mode variables. So in a coupled simple harmonic oscillator, we could still sort of simplify the Hamiltonian in terms of a summation over the normal mode vibration, but within each normal mode is nothing but a single simple harmonic oscillator. You sum over all possible single simple harmonic oscillator, and now it becomes a more complicated, phonon problems in one dimension. Okay, so it is very much a simple generalization of what you have learned in quantum mechanics, and we simply just have to sum over all normal mode variables. So now let's just take a concrete example for this one-dimensional phonon, and the simplest possible example of one-dimensional phonon is this kind of a ring shape, right? So imagine we sort of fold this one-dimensional chain of atoms and into the ring, so that the first side of the ring is actually the same as the L plus NA side, because this is called periodic boundary condition. So if you go around the ring and after end lattice spacing, you go back to the same site that you started with. So that is called periodic boundary condition. Of course, you can impose different boundary conditions, such as open boundary conditions. But for simplicity, let's just fix this much simpler periodic boundary condition, so that this displacement vector goes back to this original situation after n integer multiple lattice spacings. And how do we define this transformation matrix T that diagonalizes potential, right? So the simplest possible transformation matrix, which we call this T matrix, is nothing but the Fourier transformation, this e to the I or minus IQL, and this is just a phase that defines this T matrix. Okay, so you can see that L and Q appear in the exponent of this exponential phase, and this kind of transformation is the same as the Fourier transformation. Of course, we could define more complicated transformations for the T matrix, but the simplest possible Fourier transformation, the T matrix is just a phase, a Fourier phase. Okay, and due to this periodic boundary condition, this Q is actually quantized, because when you actually shift this L by n times A, where n is number of sites, then you go back to the same site, and therefore this Q takes the quantized value of 2 pi n divided by n times A, or this little n runs from 0, 1, 2, all the way to these integer values. Okay, so let's just Fourier transform this potential term. So first of all, let's just Fourier transform this coordinate displacement vector and momentum operator. So by plugging this T matrix here, so we could easily get this type of a transformation that takes us from this real space to this normal mode variables. And same for this momentum operator PL, we could transform this PL to PQ by the similar T matrix or Fourier phase vector. And we could also demonstrate that the potential term could be diagonalized via this kind of a Fourier transformation, because you could very easily see that if you multiply this TQL and T inverse L prime Q and sandwich this VLL prime, this potential term in real space, and you'll get this two phase vectors, e to the I QL and e to the minus I Q L prime, or Q prime L prime, so that there will be a summation over this Q, and you'll get the Dirac delta function. So that's this matrix element in the normal mode for this potential term is actually VQ Q prime delta Q Q prime, and you need to sum over Q prime. Remember that. So when you sum over this Q prime, you'll get back to VQ. Okay, so this is how you diagonalize this potential matrix in a one-dimensional atom. So this is very easy and simple, And so let me just remind you that this delta function comes about because you have two different phase vectors, right? So when you sum over this Fourier variables, you get the delta function. So now let's look at this potential term by looking at this symmetry that this potential term shows, and in particular for this kind of identical atoms sitting on this periodic structure of a ring, and you can very easily see that the potential is actually a function of the distance between these two, because this system shows a translational symmetry, and this translational invariant can be seen very clearly if you simply just shift this L by a lattice constant. Okay, so the potential term is actually L minus L prime, and which is the same as, say, L bar minus L bar prime, where L bar is actually L plus A. So the potential term doesn't change after you shift your origin by a lattice constant. Okay, so it doesn't matter how you shift your origin to any lattice point as your new origin. Okay, it doesn't matter, okay, because it shows exactly the same form, because when you shift this L by the same amount, so you also shift this L prime by the same amount. So when they are subtracted from one another, so you don't see that shifts anymore. Okay, so this is pretty much understandable, because if this is identical atoms on the ring, so it doesn't matter which orientation that I see this ring, right? So I could look at this ring from the bottom or on the right or on the left, whatever, because they are all the same. And therefore the potential energy should not depend on the origin of that ring. As a result, the potential term is just a function of the distance between any two atoms, right? And which I call this capital L as the relative vector between L and L prime. So later we will take advantage of such a translational symmetry of the potential term. Okay, so let's take a short break. When we come back, we will continue trying to solve this simple phonon problem on the one-dimensional ring. Let's take a short break. Okay, so let's continue. So after introducing this periodic bounding condition and the Fourier transformation for this T matrix, which diagonalizes potential term, and we could show that this V of Q in normal mode coordinate or in Fourier space is given by this sum over L and L prime with this e to the iq dot L minus L prime times V or L prime, that kind of a Fourier sum. And we know that this potential term shows a translational symmetry, meaning this LL prime matrix element is nothing but the distance between this L and L prime. It's a function of capital L, where capital L is defined as the distance between these two positions, L and L prime. So that V of Q is nothing but summation over L and L prime, e to the iq dot capital L and V capital L, right? And 1 over n. And you could get rid of one of the summations, say L prime, because this capital L is actually nothing to do with the one of these variables L prime, so you could safely just sum over this one of these variables L prime, so that this is given by e to the iq L times V capital L. And that is the great simplification of this, say, V of Q, the Fourier transformed this potential term. So now let's further simplify this potential term by considering just the nearest neighbor coupling between these two atoms. Namely, Suppose this is just a spring connecting these adjacent atoms, where this potential is just imposed on the neighboring sides, which means that this, this side, this motion of the side L, only the potential for this side L is only a function of L minus 1 and L plus 1, okay? Because this is taking us the nearest neighbor interactions for simplicity. Of course, in the real materials, everybody affects everybody else, as I mentioned previously. But the dominant factor that contributes to this potential term comes exactly the nearest neighbor, interaction. Okay, so therefore we consider Hooke's law, which involves only adjacent displacement vector, which is summing over L, 1/2 of spring constant K, multiplied by YL minus YL plus A squared. Okay, so this is just a nearest neighbor interaction. Suppose that this is the simplified potential term, and it turns out that this kind of approximation works pretty well to explain many phonon features in solids. Okay, so let's just expand this, Hooke's law for nearest neighbor interaction, and we could just square this, and you get this, 3 terms: YL squared, YL plus A squared, and minus 2 YL plus A, with a summing over L. So we could simplify this because, when you sum over L, YL plus A squared, we could simply just shift this L by minus A, so that this YL plus A squared, after summing over L, is the same as YL squared. So it is a factor of 2 in front of YL squared. So that just greatly simplified this potential term like this. So this simplified VLL prime shows 3 values depending on whether this L is actually the same as L prime, which is on site. When this L is the same as L prime, VLL prime is actually 2K. And on the nearest neighbor size, L is different from L prime by plus minus A, then this dimensionless element is actually minus K. And if neither these two are on site nor on nearest neighbor size, and this potential is actually 0. So that is precisely what we call the nearest neighbor interaction. So we don't consider the interaction between the atoms further from the nearest neighbor size. Okay, say a second neighbor. So we assume there is no interaction between the atoms on the second neighbor. So of course we ignore this kind of a long distance interaction, which is some sort of approximation. But as I mentioned, this approximation works pretty well in order to capture the main features of the phonon physics. So let's just Fourier transform this VLL prime into the normal mode or Fourier space V of Q, which is nothing but this kind of summation. So the first case is when capital L is actually 0, where L is actually the same as L prime. So remember, this capital L is nothing but L minus L prime. Okay, so when they're on sites, when there's 2 atoms are the same atom, then we get matrix element V0, which is 2K times e to 0, which is 1. Okay, so this is nothing but 1. And we have 2 other possibilities. The first one is when L is actually L prime plus A, you get VA, which is minus K e to the IQA. And the final possibility is that when L is actually L prime minus A, so that you get minus sign in the exponent of the exponential factor, but the other, say, prefactor is the same. So you denote this term as V minus A. So you'll simply just add these three terms together, you get 4 times k times sine square qa over 2. So this is very easy because you get what? K 2 minus e to the I qa minus e to the minus I qa. Okay, so the last two terms can actually be combined to, say, the cosine term, right? 2 times cosine qa, and with the minus sign. So this is k times 2 minus 2 cosine qa. All right, so you could just use your knowledge to, for the sine and cosine function to simplify this 1 minus cosine qa, which is 2 times sine square of qa over 2 with another prefactor, so the prefactor should be 4. Great, so we're almost done. Then this frequency, so-called normal mode frequency, omega q, is defined as the square root of vq over m, which is nothing but the prefactor times sine qa over 2. So this is a very important result because remember, this omega q represents phonon frequency, and if you multiply this omega q by h bar, this is just a single phonon energy. Namely, we actually quantize this kind of lattice vibration in terms of a normal mode vibration, and each normal mode for a different value of q, you get a different frequency omega of q, and the energy h bar omega q, which is just a quantized single phonon energy. And the way that omega q depends on this q is called the dispersion relation. Dispersion, because it tells you that the phonon frequency or energy as a function of this momentum q. Okay, so different momentum q will lead to different excitation energy or frequency. For example, when q is actually 0, you get no energy or frequency being 0, corresponding to the 0 momentum q. And at these two endpoints of this first Bernoulli zone, you get plus minus pi over Na, and at this zone boundaries, you get the maximum value of this omega of q. But in between this, you get this kind of a fan shape of a sine qa over 2. But of course, this is actually the absolute value of the sine q over a, or qa over 2. Okay, because you can very easily see this. Okay, so this is square root of the sine square of qa over 2. If you remove the square root and cancel by the square of sine, but you still need, put the absolute value here, right? Okay, and that's why you get positive values for the negative q. Okay, because there's an absolute value here, which means that the phonon frequency is always positive, and this phonon energy is also a positive energy. Okay, so that's the complete story of this one-dimensional phonon periodic ring. We could generalize this kind of study to the higher dimensions. For example, the three-dimensional lattice, which is more realistic, in terms of this real materials. So let's take a short break. When we come back, we will generalize this, one-dimensional phonon study to a more realistic three-dimensional lattices. Okay, so let's take a short break. We have studied phonons 1D lattice on a ring with a nearest neighbor potential term, and which allows us to simplify greatly this calculation, and we find this phonon dispersion omega q as a function of q in the form of the absolute value of a sine qa over 2. So we will come back to this dispersion later, but let's just generalize this approach to three-dimensional lattices. We can consider a simplest possible version of this lattice, which is just a simple Bravais lattice. for example, the square lattice. So I'm just showing a 2D version of the 3D lattice. Imagine that you have this third direction, coming out of the blackboard. So for this Bravais lattice vector is a linear combination of the 3 unit lattice vectors, L1, L2, and L3, with integer prefactors M1, M2, and M3. So that is most general lattice vector on the 3D lattices. And you could define the reciprocal lattice vector G in the way that you learn this from the introductory level of solid state physics, which I don't repeat here. So the reciprocal lattice vector has the property that this e to the I G vector dot is this L, the lattice vector, is actually 1. So always it's kind of an inverse of lattice vector. And when you sum over this exponential phase vector over L, you get 0 if G is not equal to Q. This is non-zero if G is the same as Q. So, but when G is the same as Q, then summation is actually the number of sites. So when you sum over L, this phase factor e to the IQ dot L, this vanishes unless Q is actually the same as G. Meaning this phase factor e to the I G dot L is always 1. And you sum over L of that phase factor being 1, you get number of sites. Other than that, if G is not the same as Q, then this phase factor, when you sum over the L, vanishes. Okay, so that's the orthonormal condition for the real space and reciprocal lattice vector. All right, so that's just a simple definition of a 3-dimensional Bravais lattice of the reciprocal lattice vectors G. And so now we could write down this Hamiltonian for a 3-dimensional lattice vibration in terms of, again, momentum operator or kinetic energy and this displacement vector YL. But now, each of these variables, say momentum variables PL, any site, has 3 components because now we are living in the 3-dimensional world. So PL can have X and Y and Z component, right? So that's the 3-dimensional momentum vector, but also as a quantum mechanical operator. Likewise, this displacement vector YL can have this X and Y and Z components on the 3-dimensional lattice. So, kinetic energy term and potential energy term becoming more complicated because you need to sum over, these terms along 3-dimensional directions, right? If we just expand this potential term up to second order, we get harmonic term like what we did before. But if we keep expanding this potential term up to the third order, we get n-harmonic term, which we will come back here later. But at this point, we neglect the third order term in potential energy. So now this under harmonic approximation, the Hamiltonian of such 3-dimensional lattice vibration is given by the kinetic energy term in the matrix form, the column-row matrix, and plus potential energy term, which is again can be expressed in terms of matrix product. So you got, say, a row matrix 1/3 multiplied by the 3/3 potential matrix, and then 3/1 displacement column matrix. So now you can see that this is not just 3/3 matrix anymore. Instead, because we have, say, number of atoms, right? You can consider that each matrix element is actually an n/n matrix. Okay, because in the real space representation, this is a 3n/3n. Again, this column row matrix here representing the displacement vector is also 3n/1 or 1/3n column row matrix because each of the side L can take values, right, from 1 to n. So in general, if you sum over all lattice sites, this is not just 1/3, but 1/3n. So likewise, this is 3n/1. So therefore, you get 3n degrees of freedom. So we will come back here in just a moment. Anyway, so the matrix here is no longer n by n, 3n by 3n for the potential term, harmonic potential term. Okay? For a one-dimensional problem, we only need to diagonalize this VLL prime to get VQ delta QQ prime, right? In the normal mode coordinate here. In addition to this, diagonalization on the lattice side, we also need to diagonalize this, three directions, x, y, and z. So there are two diagonalizations, that we need to do. So we need to first diagonalize the site index, okay, for the potential term, and then we should diagonalize the potential term for this direction, x, y, and z. Therefore, we need to perform two diagonalizations, and let's just do this, the first diagonalization first. Okay, so which means that we diagonalize the site index for the potential term, but keeping this, x, y, z, components of this matrix elements as they are, and for the second diagonalization. So let's just, do this first. Again, we could perform the Fourier transformation that we just did for the one-dimensional ring or a chain, and in the same way that we could define this unitary transformation T matrix as the Fourier coefficient e to the I q dot L, and we could transform this displacement vector and the momentum operator from this real space to the normal mode basis. And we could follow the same approach that we did for a one-dimensional case, and without repeating these procedures, we expect that we could have such a matrix element diagonalized. Over the first Brillouin zone, there are n independent, normal mode vectors, but each normal mode vectors contains actually three components. Remember, the oscillations or vibrations are along three-dimensional space. So in general, in real space, I have this normal mode along the x and y and z direction. But in general, this can be linear combinations of all three dimensions, but still it has three components, right? Qx, Qy, and Qz. So the normal mode, direction may points to any directions in three-dimensional space, and it has this projection onto this x and y and z axis with different values. So therefore, the total degree of freedoms is actually 3n. Also, we have a translational symmetry like we assume or we treated for the one-dimensional case. If we shifted this q by a reciprocal lattice vector, it goes back to this yq of I. Okay, so same for the momentum variables in normal mode degree of freedom, that p q plus g is actually the same as p of q, because we only care about this variables in this first Brillouin zone. So namely, this is my q, and this is the first Brillouin zone. So for all the other q values, we should bring it back to the first Brillouin zone and shift it by a reciprocal lattice vector g. So let's take a short break. When we come back, we will continue diagonalizing directions, three directions, x, y, and z, follow the diagonalization on the site. I mentioned that we need two diagonalizations to fully diagonalize the Hamiltonian matrix, and the first diagonalization is to perform the site diagonalization, where the VLL prime could be diagonalized on this, say, Fourier space or normal mode variables, and assuming that we have done that because we already did this for the one-dimensional case, and we could write down the remaining part of this Hamiltonian after this first diagonalization. Namely, we could rewrite this summation over the site index in terms of the summation of a normal mode coordinate q. Remember, this q can take three values pointing to a three-dimensional direction. So we have this, in this normal mode variable, this kind of a kinetic energy term and potential energy term. So for each given normal mode Q, we really have this 3 by 3 matrix. But of course, when we sum over all this Q, you still go back to the 3m by 3m. But for a fixed Q, we don't need to worry about the side diagonalization because we have done that already. So the remaining job is to diagonalize 3 by 3 matrix along this spatial direction, and we could borrow, this kind of a rotation of this axis, coordinate axis, from the rigid body rotation in the classical mechanics. So the goal is to transform the coordinate to the symmetry axis, namely this kind of rigid-bodied, symmetry axis. So we could perform a basis transformation or coordinate transformation, a rotation, so that the symmetry axis actually is the axis of rotation. This could be done by a proper rotation of the coordinates, and we could perform such a coordinate transformation or rotation by applying such a kind of formula that we sum over all possible displacement vector, capital R, which is a difference between L and L prime vectors, and we multiply the real space potential term by this kind of a Fourier phase vector e to the iq dot r, and then we could imagine that we could sort of rotate the coordinate in such a way that this 3 by 3 matrix actually shows non-zero matrix elements only along the diagonals and vanish along the off diagonals. So in other words, we could start from this VQIJ and rotate this coordinate basis x, y, and z, and such that the 3 by 3 matrix is diagonalized. And so as we did for this rigid body rotation, we can define this kind of a new rotated axis by this kind of S1, S2, and S3 unit vectors, which represents the this kind of three-dimensional unit vector, which is the symmetry axis that corresponds to this normal mode in the x1z axis. Okay, so by rotating these coordinates, we are able to find this normal mode for kind of a rigid body rotation like axis, and we denote these three unit vectors by S1, S2, and S3 vectors. And these three directions are called phonon polarization axis, which represents the normal mode vibrations in three-dimensional space, where this S1, S2, and S3 are simply linear superposition of x, y, and z based on the condition that we can diagonalize this 3 by 3 matrix. Okay, so assuming that we can do this, and we certainly can do this, right? So after we diagonalize the real space coordinate and also the side diagonalization after the Fourier transformation to the normal mode variables, and we have two different kinds of normal mode variables. One is the Q variables, and another is actually the S variables. Remember, the S represents the directions of phonon polarization. Suppose the phonon polarization is along, say, x1, S1 direction, which means that the normal mode vibration is actually along that direction. And same for the S2 and S3. All these Q and S variables are independent of each other. Namely, we can have all different types of the, say, momentum variables and the phonon polarization. Suppose this S vector, which is a phonon polarization, is actually parallel to this momentum q, then we call this longitudinal normal mode. And if S is actually perpendicular to q, we call this transverse. So the longitudinal normal mode refers to the situation where the momentum is actually parallel to lattice vibration. Okay, so meaning the direction of the momentum is actually along the same direction of the lattice vibration. Okay, but there is a different types of vibration where momentum transfer is along one direction, whereas the phonon polarization is along another direction. So we will give you an example of such a transverse mode in just a second. So then we can follow the same approach that we did for the one-dimensional phonon, and we could find out the dispersion relations like before, except now this diagonalized this VQS shows three different values, right? So in general, say VQS1 is not the same as VQS2, it's not the same as VQS3. So we could also follow the same approach that we did for the one-dimensional case, define this phonon operator A and A dagger, but now this A and A dagger, in addition to carry this momentum variables, normal mode variables, it also carries this polarization information, S. Since this matrix element shows three different values, in general can have three branches of dispersion relations for this phonon frequencies versus momentum. Okay, so we can sketch these three dispersions like this. So starting from the lower branch, this is omega QS1, and in the middle omega QS2, and on the top omega QS3, depending on the value of these three values. Okay, potential turn along the diagonal axis, so that the full Hamiltonian could be quantized in a similar way that we did before, except now we should not only sum over this Q variables, but also we need to sum over its polarization directions. So let me just give an example of this longitudinal and transverse motion. So for longitudinal, as I mentioned, lattice vibration and energy propagation or momentum transfer is actually along the same direction. The Q is actually in parallel to S. This is longitudinal, meaning the lattice vibration is along this axis, and so is the energy propagation. But there is another transverse type of propagation. Is this? Suppose the lattice vibration is along that direction, which is perpendicular to the direction of the energy propagation. So this is called transverse, meaning the atoms are doing like this, but in an alternate fashion, that this orange directions is actually perpendicular to the yellow direction, so that the energy is actually propagating along this yellow direction, but the actual vibrations are along the perpendicular directions. And that this is the case for a light propagation. Remember, we have this, right? So this is, say velocity direction. This is, say, E, electric field, and this is the magnetic field. So you could very easily, go back to your general physics 1 concerning the propagation of light. You could very easily see that the electric field and magnetic field are propagating perpendicular to the direction of the speed of light. All right? So this is the example of a transverse propagation. Okay? So here we have a similar situation that, this lattice vibration can actually go along one direction, whereas the energy can actually be transferred along another direction. So we will talk about this in our next lectures. In general, we have the 3 phonon branches for a simple Brav's lattice, but suppose we have kind of a more complicated situation where we have 2 different types of atoms, type A and type B, so that they could actually interconnect it to each other to form a more complicated sublattice structure. Suppose we have 2 sublattice structures of the lattice, and we could have 6 branches of the phonon modes, and 3 of them corresponds to the acoustic phonon, and another 3 are called optical phonons. So we will talk about that next time. But here, I want to point out important features of this kind of a phonon mode is that when this momentum is actually very, very small or weak, this omega is almost linear in relation to the momentum. So this linear dispersed relations, when Q is small, plays a very important role to actually understand the low temperature properties of solids, concerning the lattice vibration. So we will come back to this linear dispersion phonon mode in the later part of the calculation. So that's about today's, and we will continue on Wednesday.